Today we have 3 talks. The first will be over the mpl-hep project. Then we have one over boost-histogram and hist. And we'll finish with one over Aghast by Pivarski. So Nick Smith, I think we're ready for you to start. Nick, are you there?
Oh, I was muted. Okay, sorry about that. I'm good now. Jim just came to my office. So yeah, I'm here to talk about this project that sort of formed in the last couple of months with just the idea of trying to consolidate the various efforts amongst people trying to work with matplotlib in our field. And kind of the common theme amongst everyone is that we have one particular niche that isn't really covered by existing sort of matplotlib, is that we like to plot pre-binned histograms a lot. That's basically all we do. And also it appears that no one else does this regularly, so there's not a lot of tools. Of course, basically any other thing you might want to try to do with matplotlib is pretty well covered. If you want to draw lines, no problem. You want to draw boxes, no problem. Basically everything. You want to draw a map of Western Europe, no problem. But pre-binned histograms is a little icky. And it got discussed a bit in this issue that I link here, and sort of the conclusion of that discussion is the developers would be amenable to us providing some sort of wrapper via either helper functions or just providing better documentation on how to do this. And so we started putting together some notes in this Google Doc that reference existing attempts to do this as well as some of the goals. And there's a Gitter channel within the pi-hep or scikit-hep, one of those Gitters, to talk about this. So I'm going to just dive into what a helper function can do and what a gallery might look like, and then kind of come to a conclusion about what the plans are. So in matplotlib, basically the idea is if you want to do something that isn't part of the existing tool set, you write a function signature that looks something like this. You pass an axes object, which is so the matplotlib equivalent to a tpad, roughly. And you communicate all the styling by just passing large dicts of what kind of parameters you might want. And the idea is the function draws things onto the axes and then returns the objects that it added. And this example here is just based on the matplotlib coding style document. So I've tried this. I tried to generate a sort of general 1D plotting signature inside this Fermilab column analysis tools package, and it's heavily intertwined with the histogram object that's in that package. And I'll get to that a little later. But I don't want you to just read all this code in real time, but the point is, you end up providing a lot of parameters, but I think still not an unreasonable amount of parameters. So this concept of a helper function seems to work pretty well. And of course, since all the primitives that are drawn are returned in the dictionary, you can always go back and tweak things if you need to. Sort of the result of that is this sort of user-facing API that you see on the right here, where you have a histogram object that's possibly multidimensional, and you project it down to the dimensions you want, and you call plot. The thing is, though, I don't think this is in scope for mpl-hep, because this is very tied to the histogramming library itself, and it's not really just a visualization thing, right? You have to know that, like, the process means a certain thing, and you have to, go into the histogram object, get labels and such. I'm not sure if this belongs here or not. It's sort of up to the community to decide. But one option here is we don't necessarily have to provide this kind of API at this level. Maybe a higher level library would provide this API, and this just makes the process of getting things into Matplotlib easier. So that's kind of where I go with slide 5 here, is the gallery concept. And this seems to be popular in Matplotlib, is they provide a library of, functional primitives and leaves users to do whatever they want, and just provides sort of examples and guidance. So I tried to do that. I tried to put together a IPython notebook just with a couple different plot styles, and I've been asking people to come by and contribute their styling and their ways of producing plots. And I tried to go through all the previous libraries that were discussed in the Google Doc and try to synthesize all the different tricks that each person has found into sort of a cohesive unit. And I think I got most of them, but maybe not all of them. And I think the goal of this is just to try to, play code golf, sort of try to, what's the most efficient way to get things in and out? What's the most idiomatic way to get things in and out of Matplotlib? And on the bottom just kind of shows a few of these examples, which I think covers, maybe like 80–90% of HEP figures, right? Modulo styling choices. But one thing I'd like to do is try to figure out how to use restructured text and Sphinx, which is sort of a document auto-generation tool that Matplotlib uses pretty extensively to provide gallery that is easier to maintain in version control, because of course the Python notebooks aren't the easiest thing to version control. So that's there, and I'm inviting anyone here to come participate. One thing that we did notice is there's no good way to sort of make a skyline or step plot with edges without kind of this hacky extra step of adding appending the last bin to the end so that the plot draws correctly. And so one possible improvement to Matplotlib itself is to implement this step equals edges sort of style, which reduces the code footprint a fair bit in our use case. Other ideas that I've thought of that this package might be able to provide is styling. Of course, this is largely experiment specific, such as CMS has the infamous TDR style. But Matplotlib provides, the same sort of style sheet mechanism that Root has with T-style, and we could provide, pre-curated ones to the community if that seems to be useful. And then the other idea is that a lot of people are coming from, possibly several years of experience with Root, and it would be a lot easier for them to transition if they had a sort of Rosetta Stone to translate the terminology they're familiar with to the new terminology. And that's something that this package could host, for example, just as a markdown or restructured text document that people could come and contribute their idioms in Root and then the corresponding idiom in Matplotlib. So I think that would be, useful activity in this project. So in summary, Matplotlib obviously can plot pre-bin data. That's not surprising. You have to do some workarounds, and they've been documented in this mpl-hep repository. And I encourage anyone here to has found things they had to work around to contribute them. And longer term, I'd like to figure out what kind of API is needed, if any, and try to abstract these common patterns into that API. And in the meantime, the concrete plan is just to try to get step equals edges into Matplotlib, compile the gallery, and start to work on this Rosetta Stone. So that's mpl-hep. Any questions?
Hey, this is Gordon.
Hi.
I really like the idea of the gallery, and also the sort of the Rosetta Stone. especially for things that are more focused on high energy physics, because there's certainly things that we try to do that are not that common out in the real world. And then also this idea of trying to get a set of styles put together. I think that also is key. I know, for example, in Atlas, that if your plot doesn't comply to the style, then it doesn't get published. And I know people have taken the plots, their data from the Python world, and then run the root plot macros in order to get an officially blessed looking plot. But I wonder also if many of these things should be split out into small projects, one for the documentation, one for sort of the Rosetta, one for the Rosetta Stone, one for the examples, things like that, as opposed to trying to gather them all under a single project name. So each thing is small and very focused on the task it wants to do.
I mean, that is always a good idea. I've sort of assumed that the splitting is more a product of the number of active developers than, say, the functionality.
Good point.
So certainly if a lot of people come on board and we find that we can enable splitting these finally, then maybe that could be done.
Well, I suppose they could still be split finally, even if it is one or a few people doing it. We're just talking about giving different names to each of these steps, like making the gallery is a different thing from upstreaming edges, which is a different thing from the Rosetta Stone, and just help have different names, different GitHub repos and such.
Well, I mean, some of them really aren't even a repo per se; they're just a task that needs to be done.
Mm-hmm.
But
yeah, upstreaming edges is not a repo except in as much as a PR is a fork. Yep. But the other two might be like the gallery could be hosted on GitHub.io.
Right. Well, so the way I see Matplotlib done is they can't quite find where exactly their source is, but they have a GitHub source within the Matplotlib repository itself, and they have a separate GitHub.io with the Sphinx compiled documents. So someone manually runs the conversion, and then I think commits that. So
yeah, you can do that, although GitHub does recognize restructured text now.
Right.
And if you're just beginning this and you don't intend to merge it with the rest of the Matplotlib, then you might want to shop around for a markup language that is easier than restructured text. There's no reason it needs to be that one, unless you're trying to merge in with the Matplotlib documentation, which is all restructured text already.
I mean, there are certain advantages to merging it with Matplotlib,
okay.
But I don't know. I haven't really thought if that's the goal or not.
I was also just going to echo Jim and say that, I mean, for PyHF, we write most everything in Markdown and then just use the Sphinx converters to convert it all to restructured text, and it works pretty well. I mean, there's very few things that we've actually had to kind of manually figure out how to deal with. But I mean, if you're already good with restructured text, then yeah, go for it.
Pretty much not, actually.
Okay, well then I would just say go for Markdown.
Yeah, okay, that's good to know.
Yeah, I'm happy to talk about that if you have questions. I did just kind of have one further question. So I'm on the binder for mpl-hep, and so just to try and you already mentioned this in your talk, so I'm sorry that I'm not totally cracking it. But so the point of the mpl-hep, as you referred to it, like as the package, like this is right now just kind of one central area to collect all the stuff that will then be split out over time. So I mean, the goal, you've nicely linked to both the getter and also to the respective issue on the respective issue where this discussion has happened, but the goal is eventually, beyond some API changes, to get some of this stuff fully back into Matplotlib at the end of the day, or is it really just that we're going to end up writing a whole bunch of helper functions that people are going to have to, copy and paste themselves over and over and over again?
Well, so I don't think the helper functions, if we write helper functions, let's put it that way. First of all, it's not clear if we will, but if we do write helper functions, I think they would be part of a repository named mpl-hep that could possibly be hosted within the Matplotlib organization. They do that. They've offered to, and people would pip install it to get the
Okay, so it would be its own. It would be its own it'd be its own library unto itself that is specifically designed to kind of be like I'm going to use this word improperly, but plug-in for Matplotlib.
Yeah, in fact, they have a term third-party package.
Okay, great. All right, thanks. That clears up my questions for me, so thank you.
Yeah, but as of the moment, it's not clear yet what kind of helper functions would be useful. There's a bit of a diminishing returns of how simple the wrapper is, and
sure,
we're not trying to be Node.js here or something.
I think right now the most important thing is to collect examples of what people want to do, or what sort of plots people can come up with, what styles they need.
Exactly.
And one way to do that is to get some folks from the various experiments to spend 30 minutes going through several different physics groups to look at the plots that are just shown on Indigo currently, and you will immediately have a whole example of things that people will try to do.
Right. Yeah. I've covered a few of the bases on slide 5 so far, but there's plenty more that aren't covered yet.
Nick, this is Ben. We've spoken a bit on Gitter.
Right.
I had a few points. I think you specifically asked where's the gallery for Matplotlib. It's actually where's the documentation hosted? It's actually in the repository for Matplotlib, in there directly. So if we're thinking about like following their model, then it makes quite sense to me to put our gallery inside the mpl-hep package. That was the first point. The second one was, I think, the things like the style sheets and maybe other things like actual technical solutions, we might want to look at RootPy, because I know that RootPy does do a few things already to connect between, to make one function look like the same call to a root histogram, but then actually do it on Matplotlib. So I haven't actually played with that enough. Maybe I might be missing something there, but I think that we could look at them. I know they have a style sheet thing, and I know they also have an aspect which is, they've already got a few experiment styles in there, so we could maybe just look at maybe some of that should be moved out so that it becomes into this package, or maybe we just use it as inspiration or something. I don't know. I'm contributed to that, but that's it. And then the third point was, it seems to me like a good way to push this forward would be to have a small 2 or 3 day, 1 or 2 hackathon, workshop type thing. And I've been specifically interested in trying to put a few of these sort of very focused groups together. And maybe this would be an interesting way to move this project forward, so we get anyone that's interested, 10 to 15 people or whatever, connected remotely largely, or if we're all at CERN or firmware or whatever, but then sit down and try and throw bits of this together, galleries, the package, whatever. I don't know what you think.
Yeah, I mean, that would be great. So far it's sort of been just me kind of looking around, seeing what's there and trying to plug things together, but more viewpoints is the only way to a solution that's going to be accepted broadly.
Mm-hmm.
Just for reference, I linked to the example that was just mentioned about RootPy, including some styles. I linked to that in the Indigo chat.
Okay, thanks. Yeah, I'll add that to the Google Doc. Okay. Thanks, everyone.
All right, thank you.
So, hello?
Go ahead.
I wanted to say something about the previous talk, sorry. So I have some of these plotting tools already in my private library, Pike. For example, making these nice boxes that sometimes people do to represent systematic errors around the point. So this could go into this mpl-hep, for example. And otherwise, I like this idea of collecting the plots first, and then this gives an idea of what to do. Another thing I wanted to ask, is this Rosetta Stone supposed to be just a document, or we could also make a module that's called Rosetta, which then has, I don't know, T-pads and T-canvases, but those would actually represent the corresponding objects.
I'm a little resistant to the latter option.
Maybe for good reasons.
Yeah, I think it should just be a document.
Yeah. I think also, you can make it easy for people to switch, but then, at some point you want them to learn a new thing, I suppose. So, yeah.
Right.
Okay. I just wanted to throw it out. I'm not so sure myself whether it is a good option.
Yeah, I guess that's sort of the direction that RootPy went, right?
Okay. All right, so the Gitter channel was linked there, I believe, so feel free to continue discussions there. Let's go ahead and talk about boost-histogram and very briefly about hist. Okay. So let's start by giving a quick history of histograms in Python. I think you'll see this again in the next talk. So the current state of histograms in Python, there really are a lot of different packages out there that try to do histogramming in some way. The core library NumPy does have a histogram set of functions. Historically, these were a bit slower than ideal. At least the 1D ones have become a bit faster in recent releases. And it did not have a histogram object, which is really what we like to see in HEP and think about in HEP is combining and working with histograms as objects and plotting them, etc., rather than manually keeping track of everything ourselves. And plotting was separate. So plotting was part of matplotlib, and then in matplotlib, you either had to do the histogramming and the plotting, or connecting the two had some challenges, such as the step issue we saw in the previous talk. So there have been a variety of other packages, but each of these has really had a very narrow focus. They focused on speed, such as fast histogram, just trying to make NumPy faster. Some of them are focused on plotting or having this nice language to put everything together. Many of these are abandoned. The smaller ones there tend to be less used. And they've had some issues with designs and distribution. Many times they were trying to do everything in just Python or falling back to NumPy. So really, I think the four things that we need for a good be-all histogram library would be a good design. It should be really easy to manipulate, plot your histograms. It should be flexible. It should allow lots of different options, the various things that people may want to do, like growing histograms or sparse histograms, things like that. And it should have good performance. Single-threaded filling should be fast, and ideally it should support multi-threading filling as well. And should be very easy to distribute. So we'll be talking sort of about these four things again. So if we look at sort of the outline of the plan we have for histogramming in Python, there we go. So these are the core histogramming libraries. So you would have boost-histogram would be a core histogramming library. There could be others such as root. These can talk to Aghast, and you'll hear about Aghast in the next talk. And Aghast will connect to the more front-end like libraries which handle plotting and that sort of thing. And that's where hist falls in. You might have different plotting from mpl-hep and other things, and other libraries there. So first, let me mention in one slide what boost-histogram is. This is the C++ 14 library that's part of Boost. Apologies to Hans for condensing all of boost-histogram into one slide, but I tried to. It's a header-only library that's inside the Boost libraries, and it was released just last week. So Boost 1.70 had boost-histogram in it. So it's now officially a Boost library. As a reminder, Boost is the next best thing to the standard library in C++. It was often a staging area for the standard library. So sort of inspired by root and histbook and a few other things. And it has this consistent language to build histograms, and it's nice. All the histograms, 1D or 2D or ND, all are sort of in the same, written in the same language. You have axes here, and there's a variety of different axes types. And then you have, you can combine these, 1, 2, or however many you want. And then it creates this storage here. A boost histogram itself supports static and dynamic storage, so you can have an entirely static histogram if you want. But we're talking about Python, so we'll talk about dynamic storages. And then you can have accumulators in them, and that handles what you actually increment in each cell, whether it's just an integer or if it has a weight to it or various things like that. And histograms, as I said, come in a variety of different things. They can optionally have underflow, overflow. They can optionally grow, things like that. So boost histogram with the dash is the Python bindings to this library. So this was originally part of the design of boost histogram. It was supposed to have Python bindings. There were original bindings that were based on boost Python, but they were hard to build and distribute. They were somewhat limited. So I've been developing new bindings with Hans, with the original author of the library, here as part of scikit-hep. So it's in this boost histogram repository. This is a zero dependency build. It puts in everything that you need, and it only requires a C++ 14 compiler, and it uses PyBind 11. And so again, we're going to be looking at these four key topics that I think the library must be able to address. So for the design, it tries to stay as close as possible to boost histogram, but to still be somewhat Pythonic when where it needs to be. So you can see a comparison of the C++ code that you would use on the left and Python on the right. It supports, it's already fairly well tested. It's a few hundred unit tests. It's running, they're running on Linux, Mac, and Windows. And it supports Python 2.7 and 3.4 plus. So that may change to 3.5 plus if there's ever a reason to. As I mentioned, all these histograms have the same interface. There's no special interface for 1 or 2D, unlike root and unlike NumPy. So here are some examples of manipulations, the ways you would work with a histogram. These are the things that should make Irish physicists happy. You can simply sum two histograms together there. You can scale them, projections down to axes are trivial. You can count up the contents. You can access these axes and various axes properties. Filling is done here with this call operator, and this currently matches boost histogram. And then there's a couple of special fills here for threaded fills and atomic fills, which are just two different ways to do a multi-threaded fill. And then you can also directly convert this to NumPy. There's no memory copies that happen here. You can call .view, or you can actually just pass it straight to NumPy, and NumPy understands what that is. So it's also very flexible. You have a variety of different axes. These are the different types we have so far. You have regular axes. You have these circular axes that wrap around. You have variable spaced binnings. So these are ones that have irregular binnings. In traditional NumPy and in root, these two are generally the only ones you have. You can also have integer bins, which are a bit faster and easier to make. And then you can even set up your own categories. And currently for integers, and others may come along. There's a variety of different storage types here that you can then combine with those, integers, doubles, and then some of these other histogram storages are being worked on. Okay. And as I had mentioned before, performance is important, so let's take a quick look at the performance. And this is based on the performance post that I have here that you may have seen linked in at some previous point. So this is a similar setup, but this time we're looking at boost histogram and comparing it to NumPy. So I'll just go through this first one in detail. This is a dual-core system, so ideally we should be able to get between 2 and 4 times faster than the base speed, roughly 2 times. Here's the speed for NumPy. The storages here, they're actually all unsigned integer 64. Those are just the names that you would give to the underlying system, NumPy or boost histogram. And you can see that if you allow any possible axes, and you actually have to force the library to do this, then it's a bit slower than NumPy. But if you just use a regular axis, which on a 1D histogram, the only thing that really makes sense. It's a bit faster than NumPy, almost twice as fast. And while for this sort of a histogram, atomic fills don't really help you, the threaded fills are fairly nice. You can get an extra roughly factor of 2 for the 2 cores, which is nice. If you look at this on a 24-core machine, then again, this is a relatively dense histogram. It has 100 bins, but you can still get a nice speed up over the base speed. Here we're not quite as fast as NumPy, but very close on a single thread. And on a K&L machine where you have a lot more cores and you really would like to be able to use those, you actually can use those with this. You can get up to about 8x speed up. So I'll just skip to the summary here because I have a summary of these tables. So the maximum speed ups that we saw for a single core, we're able to get the speed ups you see here on these first pairs, and then we're able to get up to. So if we have a Linux 24-core machine, we can get up to 20 times faster than NumPy for a 2D histogram, and up to 36 times faster if we have 64 cores. So this is quite nice. And the NumPy 1D is really hard to get much faster than because it's been very well optimized, especially for regular binnings. And also for the Linux machines, I'm using Anaconda, where you may get a few extra optimizations in NumPy. And if you mix your types in boost-histogram, generally only with 2 or more axes, if you have different axes types, then you get a small performance degradation there. Distribution is another thing. This is something I think it's really important that we nail this. If anybody writes pip install boost-histogram and it doesn't work, then they're not likely to want to use our library. So in support of this, I developed the mini Linux GCC 8 Docker image that we have here in scikit-hep. And I've been working on this, and this is all quite new. I've been working on it in the last few days, but it's already coming along quite well. So the mini Linux, I've actually got that working. I can install it on any computer that supports mini Linux. Mini Linux does not mean all Linuxes, as you may have found out if you ever try to do pip install on some of the more exotic Linux distributions, but it supports most of them. And the more exotic distributions actually just tend to work because they tend to have newer compilers. So this really covers pretty much all Linux. If you can support mini Linux and then have an out-of-the-box zero dependency build, even for a newer compiler, you get all the Linux distributions. Mac should be pretty easy, and Windows is mostly there, and it builds out of the box on Windows as well. One thing to note, there are some discussion questions here for afterwards, but Python 2.7 is really challenging to support on Windows because it requires an incredibly old compiler, which of course doesn't support C++ 11, much less 14. There are ways to work around that, but I think for initial release at least, I don't think it's important to do that. We may not support Python 2.7 on Windows, but I'm willing to hear other opinions on that.
That's a good question. At this point, just while it's up, why do you have your own mini Linux? There's a mini Linux that people normally use for binaries in Python. I'm just curious why this one's in scikit-hep. Like, what was missing?
It needs GCC 8, or it needs GCC newer than 4.8. The official mini Linux uses the official CentOS 5 compiler, which the latest version they provide is 4.8. So mini Linux, that's why they're developing mini Linux 2010. You have to build GCC yourself if you want to go past that. So I did build GCC myself, and that's this mini Linux Docker.
Okay.
It produces a binary that is a mini Linux. The one downside to this is if you want to talk to it at the C level, then you'll need to use something that's compatible with the GCC 8, obviously because you're building a GCC 8. So you'd have to do something similar if you want to talk to it at the C level. And we may experiment with some things that will do that, but they will also be inside the same development, and hopefully we'll use this. And hopefully the mini Linux 2010, which is rolling out sort of this last 2 weeks, hopefully that will be out, and then this will not be very important anymore. If an old version of pip, it always picks up mini Linux 1. It won't pick up mini Linux 2010. Yes, that's why. Otherwise, it does build on the standard mini Linux container. So the sdist to build straight from the sdist, that's ready. I've attached it to the meeting notes. I'm not ready to do a numbered release for a couple of reasons. That will come later this week. But if you want to grab the sdist and download it yourself, you can. You can also build it straight from GitHub with this command down here. That will take an extra minute or so because it's downloading all of the Boost dependencies as Git submodules, whereas the sdist, those are all just in there as header files. And then conda package should be really trivial. The conda compilers are all easily new enough to do this, but it's not out yet because there's no numbered version out. So for things that are not done yet, there are a few other things here that I've listed, such as there'll be a little bit of work on the axes types. I think I'll be adding separate controls for underflow and overflow, like if you want to have a radius or something like that. The unlimited storage histograms have a few issues. Unlimited storage is mostly there, but there's a couple of things that are disabled right now for unlimited storage. And unlimited storage, if you're not familiar with the boost-histogram itself, is just a storage that starts out small and then grows, gets bigger and bigger, and it can also handle an automatic conversion to a floating point type if you multiply by a fraction or something. So it's rather handy. There's a few more shortcuts I'd like to do. You currently can convert this into the NumPy style output, but I'd like to support sort of a NumPy style input so that it can be just a drop-in replacement. If you just want to make your histograms faster and you are already using NumPy, it should be a trivial drop-in. A few things with filling need to be addressed, and a few other small things. But otherwise, it's mostly there, and then this sort of work on getting the wheels and stuff is ongoing. So a first alpha release is planned for this week. And then briefly mention some things that could be discussed. Right now, the API is not the most important thing. The most important thing is making everything work. So we can discuss the API if these are the best names to have. So right now I have a plan for the boost-histogram package, and it'll be from boost.histogram. That should be relatively safe. And this is sort of what it looks like. But this could be different. So this is open for discussion. And also, if you have any, if you try it out and you come up with an interesting example, feel free to contribute that. It'd be nice to have good examples for the documentation. So let me briefly mention hist. Hist is sort of just a plan at this point, although work has been going into boost-histogram. But the idea is that hist would basically be a wrapper piece that does all of the other things that you might want to do. If you're actually using this in an analysis, you probably want to have plotting and various things like that. So these are some of the things that would be part of hist. So if it's a simple thing that you could easily add and it doesn't add any dependencies, it could go into boost-histogram. But plotting adapters, that would be something for hist. Serialization will be something that hist will support through Aghast, I believe. Boost-histogram does support basic serialization, but not to a standard format. Automatic multi-threading, so it would just pick what it thinks is the best multi-threading. Those sorts of things are things for hist. An idea's hist book itself has been archived, and then this sort of technology that went into hist book will become part of hist. So this hist will sort of absorb some of, and maybe many of it over time, the other adapters. That's at least the hope, that we could sort of standardize on a language here, and that would be part of hist. And this is really something for the community to develop. It's not just something for somebody to pick. So I need to know what you need, what you want, what you'd like. Feel free to join the development of this. This will be pure Python. It should be very easy to work on. So I'll get it started, and then I'm really hoping for contributions. So with that, are there any questions about boost-histogram or hist?
Hi, it's Peter Anisi. Can you hear me? Okay. Yes, so I'm wearing my Atlas data quality monitoring hat at the moment. And this is, so boost-histogram is something that actually is quite interesting for us in that potentially it addresses certain underlying issues we've had with the way we do things. But I was actually hoping to get a little bit more of a discussion about the underlying data model, because there are certain things, like I've looked at a bit of the boost-histogram documentation, that are things like histograms potentially taking up indefinite amounts of memory, for example, by default, which are not acceptable in the production monitoring system. So I was wondering if maybe a little bit more understanding on what the backing models are. I know that in principle you can swap them.
Henry, should I answer this? Or
Yeah, go ahead.
Yeah. So I mean, first of all, you can have a very simple storage that doesn't do that. It doesn't go to infinite size in memory. The simplest storage is the one that is basically using a vector as a backend. So you have just one number, one integer, for example, per cell of the histogram. That would be the direct equivalent of a root histogram, th1d, for example. Well, that would be a double then. So the unlimited storage is nevertheless the default because for people who don't really care about these things, it's the most convenient one where there can be a least amount of problems. It's very, very unlikely that you ever run into the case where you actually have to use the multi-precision integer that can grow to arbitrary size, because I mean, I don't know what 2 to the power of 64 is, but it's a very large number. I mean, from top of my head, I don't know. It's very hard to reach that by filling a histogram with any reasonable data set. So I wouldn't worry about this too much. But if you have a strong requirement that this can never happen, this may never happen, then you just choose a different storage, and it's very easy to switch from the default storage to another storage which doesn't have this feature, let's say.
Okay. Is there a standard recommendation for storage for sparse in multi-dimension?
I didn't understand the question. So
for sparse multi-dimensional histograms where you might effectively be defining 10,000 bins and you're only going to fill 50 of them.
Yeah.
Is there a standard recommendation? We should find a specific SDL container that maps onto this case?
Yeah, so currently supported there is, so this case is supported, and you can use any standard compliant map implementation. So you could use standard map or standard unordered map, or you could use one of the boost maps, or any other map that has a standard interface. And we don't have a recommendation right now which ones to use, because I didn't do any performance studies on that. I personally believe that that this is probably not working out so well as people think. But I mean, maybe just use case. So I'm interested actually in people who want to try this.
Okay, I mean, just to give an example, one use case is, you have a map, all the modules of some detector, and if one of them goes into error, you fill a 1 in some bin. So half the time you expect this thing to be totally empty, and then one thing might go off, and you don't want to store it as a tree. But okay, at least there is a solution, and we can look at what the benchmarking is. So.
It is quite easy to swap those out. I use integers and things. And you can also have one thing that might be particularly nice for an experiment framework is the static storage, where you have an array to the back end and you have no memory. You can have no memory allocation at all. You can have that entirely static, no dynamic memory allocation. So it does support as well.
It seems to me those options would be more difficult to get working with the Python layer. Like if you're completely free to use any STL collection, somehow the Python layer has to know about your choice.
Well, the Python layer has specific backends you don't really have.
Yeah.
In Python, you simply make it through the Python interface, so you don't have arbitrary STL tends
Yeah.
to give
Right.
because you're in Python. So those, yes, I go through and I select, and I think the list of ones I had selected. But I go through and I select, and I only do the dynamic, the STD vector basically, and a collection of different accumulators. The bindings take those.
So if someone's interested in eventually going to Python, there will be a set of recommendations. Because if you're outside of that, you won't be able to use it on the Python side.
Yes, but I don't know how you could sort of slowly transition to Python, though. Because if you're in C++, you would have a vector of values, and then if you switch to Python, you now have NumPy arrays. You're not still using your same vectors.
I mean, I suppose that you don't foresee a situation where anyone would want to pass one of these objects from some C++ layer to a calling Python layer?
I think, so I've not tested this, but I think you should be able to, so it depends on what you write your bindings in. If you're doing that, I assume you'd be in something like a root, CPP-YY powered system, and I think CPP-YY should handle boost-histogram. I don't see why it wouldn't.
So basically we would be bypassing, we would have to use the sort of native interface, quote native, native translated by some automatic binding.
Yes, it would probably not use, in that case it probably would not use the boost-histogram Python wrapper. If you did the Python wrapper, that would be of course by bind 11. And you can, it's not particularly hard to implement a new implement and register a new storage, etc. I might look and see how hard that would be to do separately from the library. I don't think it would be hard. So you'd implement your own, and then you'd register it in with the module. Yeah, you could probably implement a new one relatively easily. That's not a use case I've thought about much.
Can I ask about hist specifically? Online is not. Yeah, I mean, how much code do you actually imagine being in hist as opposed to wrapper code? Things like this slide 25, you've got the efficiency as an example. You mentioned histbook functionality coming out of histbook and into hist. So how much do you think hist would become a package really delivering code, or will it just be glue that literally just pulls these things together and it's somewhat of a meta package that a user can just do that and get?
I think a lot of code will end up getting moved here. Of course, it will pull in, and the question, big question will be on Aghast, which we'll see next, and how much hist, I believe, will talk to Aghast, and potentially it might not even talk to boost-histogram at all directly. It may just talk through Aghast. And then so some of the basic sort of glue work will be done in Aghast. Okay. But things like the histbook code, I think that will be moved into hist. It will not, histbook itself will sort of, I mean, that's archived at this point. I don't think it's intended to, any development is intended to go there. But the functionality it has will be moved over to be part of hist. So I think you'll end up with a decent amount of code eventually inside hist.
Okay.
The idea is it's sort of the collection, so any of these other packages would be able to talk to Aghast and therefore to boost-histogram, etc. But sort of the best practices, once they're collected and once we know like this is how people like to do plotting, then that will go into hist. That's the idea.
Okay.
Open for discussion.
Okay. That might be a good segue. Because bits of histbook go into Aghast too. Let's see, I want to share. I want to steal your sharing. Yeah, I took it over by force. Okay. So, I'll quickly talk about Aghast. I'll get the majority of it done by 11:30, and then we'll see how much time is left. So, know how much. Okay, so what started me in this direction, this is a slide from last summer, was I looked around and found that there are actually quite a lot of histogramming libraries out there. Henry already talked about this. And in resurrecting this slide from last summer, I noticed that I had actually commented out 8 lines so I could fit it on the screen. And there's more than that. I didn't include the ones that I've written over the years. And today you've heard about 4 more. So this is sounding like, what is a user to use sort of problem. And this was actually what steered me from developing HistBook as an end-all histogramming package into realizing that we have to take a step back and think about this more. So, because we're really not lacking for options. It's not like I had previously thought, where in the Python NumPy scientific ecosystem, we just don't have histogramming tools that are good for HEP. But we have too many. So, and more than that, these libraries are specializing. So what you've heard about boost-histogram, its focus is filling. And what you've heard about mpl-hep is all just plotting. And then we haven't even talked about fitting tools here. A physicist needs all 3. And so maybe, the hist package will wrap that all up behind a single import hist command, making it convenient. But in order to glue all of these backends together, they'll need to be able to talk about the same histogram objects, whereas currently they have to implement their own in order to talk about what is a histogram. So that's what that's the primary motivation for this Aghast library. Not exactly an acronym. It's aggregated histogram-like statistics. It is an in-memory serializable ontology of histogram-like objects. So what I mean by all of these things, in memory, the purpose is to move histogram-like data from one library to another. And from a user's point of view, that would be invisible as just part of a function call. You would say, oh, take this histogram from here and send it to here in this library and send it to the function there in that library. And somewhere in between, that histogram object will be intercepted and converted. So it's not primarily intended for long-term storage in files. So for that aspect, think Apache Arrow. If you're familiar with Apache Arrow, it's that kind of thing. For serializable, we will want to send some of this data over the network. I'll mention that in a moment. And possibly between languages, C++ and Python in particular. And so we've chosen flat buffers as a means to do that, as a serialization format. And flat buffers has a lot of nice features, particularly well suited for this sort of thing. And interestingly enough, flat buffers comes from network gaming, so it's designed for speed and small network size. The last point is an ontology. This is not meant to be a library that functions, that does things for you, like filling or plotting. It focuses exclusively on just representing the data, and therefore converting histograms to histograms. So it doesn't fill or plot them, and that's like the first sentence on the GitHub pages, in case there's no confusion. So in this respect, it's like a project that I've worked on that I've been involved in for a while. Maybe not have heard of it. Predictive model markup language describes machine learning models without actually training or scoring them, just as an in-between. So another reason why we, particularly in IRIS-HEP, in the analysis systems, are interested in library-neutral histograms is because we're developing a query service to keep large data sets inside some system while being responsive to user requests from the outside. And so in this very simple flow diagram of query comes in, does some processing, and gets a reduced output out, this reduced output has to be a form that can be transmitted over the wire. It has to be merged internally within the query system. And then when you get it out, you want to be able to not just use one histogramming library, but use your favorite histogramming library, any of them. So it needs to be convertible into any format. So these objects, they're nouns, we thought it was a good pun to call them Aghast. So that was primarily where that name came from. So what does it look like? Suppose that you have a NumPy histogram like this one here. There's a set of functions in Aghast from NumPy to NumPy, from root to root, etc. That will turn it into its intermediate form. This is a class hierarchy. The intention is to cover all the bases. Anything that you can describe in any library needs to be added to this in order to just to be able to represent it. Lots of long class names with deep constructs, not intended for end users. This is just to be so that we don't leave anything out. Here's a root histogram converted into Aghast, and you'll notice that this one is longer than the NumPy one. It doesn't fit all on one screen because it has additional requirements. You need to be able to save moments in order to preserve the unbinned mean and standard deviation that root histograms have. So really, all the features, there has to be something for that, somewhere to plug that data in. And then the real purpose of this is to go from one library to another through this. So here's an example, taking root histogram and turning it to NumPy. Even though NumPy doesn't have a concept of regularly spaced bins or overflow bins, we can shoehorn the root histogram into this form. Going the other way, obviously, you can take a NumPy histogram and then plot it in root. I'll note that it's now 11:30 in case anybody has to go to other meetings, but I'm going to continue giving this talk. This is the main thing. You've seen the main purpose of this library, converting the objects from one library to another. Okay, so now I'm going on. You need to be able to add these things. So so here's an example of adding histograms that have different structures. The one that comes from NumPy and the one that comes from root, they have a lot of different metadata. Like the root one has those moments and the NumPy one doesn't. You can still add them, and whatever you don't have in both cases, you lose. So here's the entire output. We've lost the moments because we've added it to a NumPy histogram that doesn't have the moments. So that would be the correct thing to do. Pandas there's a good affinity between the Aghast data structure and Pandas data frames. There have been some talks I've given in the past where I'm proposing the idea of using Pandas as a histogram. And I found some difficulties in doing that because Pandas doesn't assume that your data represents something pre-binned, and so it doesn't combine things quite the right way. And so that's why we made the separate library, Aghast. But it has a very close relationship with Pandas. So if you, for instance, you want to take your root histograms and turn them into Pandas, or vice versa, you can do that. So this is meant to be a common way of describing the features of all histogram libraries. So if there's a histogram library that has some feature that cannot be somehow expressed in terms of the classes that we've defined here, then we'll add classes. Flatbuffers has schema evolution, and you can add classes without breaking forward or backward compatibility. All of these are links, by the way. So if you're interested in any one of these, you can click on it. I'm not going to read this slide. This is just to try to illustrate that, yeah, we thought about all these use cases. Expressing it somewhat economically in terms of those classes. Like if you want efficiency plots, there's a special fraction binning access for that. So then that becomes a kind of binning. Collections of plots representing the same observables with different cuts, that's a predicate binning. We want to have collections of plots representing different systematic variations, it's a variation binning. So So now just a few things about if you've got something in this object and you're not immediately moving it to another form. I'll talk a little bit about extracting bin values and other histogram to histogram transformations which are not directly converting to other formats. And actually these tools for converting histograms to histograms are used in the converting code. So I'm going to use all the same example for all these slides. So this bit of text will be the same on all the subsequent slides. I make a NumPy array that's all ones except for the overflow bins are 999. And I put that into a histogram object, building this histogram object directly with the Aghast classes rather than a converter. And then if you want the counts, it has NumPy-like syntax for getting those out. So there's slices and there's multi-dimensional indexing just like NumPy. And of course, internally it uses NumPy. The choice of binning, whether it should be 0 indexed or 1 indexed to account for underflow bins, it's all 0 indexed and does not it does not include the overflow bins unless you explicitly ask for them by saying that the slice goes to infinity. That's a way of sort of shoehorning that concept into NumPy into the NumPy slicing without breaking normal NumPy slicing on non-overflow bins. Of course, you can do that in multi-dimensions and slices all the different ways. And the point of this is that is to encourage high-dimensional histograms as intermediate data, where one of the dimensions can be all my systematic variations, or one of the dimensions can be all the different control regions, and therefore make these multi-histograms that have been mentioned earlier. Slicing, projecting, and rebinning have to be very easy if you have this kind of world. So, for the slicing, we use Pandas's terminology, lock and ilock. So if you have a histogram.lock and do a slice on that, that slice will make a new histogram, just like lock on a data frame makes a new data frame. And lock uses the your user x coordinates for where the slices are, and ilock uses integer indexes, just like Pandas. And a nice feature of this way of doing things is that there is a third parameter to these slices. Slice goes from something to something, step by something. We can interpret the step by as a rebinning. And so slice and rebin in the same context. And so remember that this all contained ones. If I rebin in both dimensions by factor of 2, then we just end up with 4s. Projecting using the same kind of mechanism. We want the axis to go away, so we put none there, and that sums over the dimension. And so note that slicing, projecting, and rebinning are all aspects of the same operation. So if you give it a slice, you slice from something to something and rebin by, and this looks an awful lot like slicing in Python or NumPy. And projection is just you send one of the axes to none. And lock is like the x coordinates, ilock is integer coordinates, just like Pandas. And then going a little further with this, you could do NumPy advanced indexing to even do slices that leave gaps. If we ever had a library that we would be saving things to where you would have histograms with gaps. So the summary is that instead of writing n times n minus 1 over 2 converters among n histogramming libraries, we create one ontology, including the concepts of all of these libraries. And then we only have to write n converters. to convert the end libraries into and out of it. This allows Python histogramming libraries to specialize, so no one library has to do it all, but a user can get it all. And it provides a reduced output format for future query service without tying that query service to any particular histogramming library. The histograms are n-dimensional and slice, projected, rebinned like NumPy. And in our choice of flat buffers, it was because it has for serializing this over the network, is because it has a minimal wire protocol, can be selectively deserialized, kind of like in T directory. If you want to pull one object out of a directory, you can do that with flat buffers. You don't have to deserialize the whole thing to get anything. It has schema evolution, so we can add classes as we find that we've forgotten features. And it's multilingual. So actually, most of the development in flat buffers is done in C++. So this ought to have a C++ library. What we have right now is a pure Python library. So that's what I had to say about that, and looking for questions. Any questions?
Hi, Jim. I have a question.
Mm-hmm.
So first, it's an obvious question. So you provide views to the internal buffers of these respective libraries, or do you convert? I mean, do you copy the data from, let's say, a NumPy histogram to your intermediate representation?
Always view if possible.
Mm-hmm. I guess it's hard, for example, to go get the buffer out of a root histogram.
Yeah, although I have included enough hooks that it would be possible to view a root histogram without copying.
Okay, that was the one question, and then so I mean I understand the aspect of having in-memory serialized transformations between different libraries, but I mean you also could provide some. I mean, you provide tools to work with this intermediate representation, in particular the reductions. So, right. But I mean, yeah. So the question is, what's the scope? So should other libraries? I mean, other libraries could of course use Aghast features instead of implementing rebinning and projection and so on on their own. They could just use Aghast for this. But I mean, it seems to break what you initially promised, being a conversion library. So can you maybe comment on this?
Yes, that is an excellent point. It's something that that I've thought about myself, actually, because it could be preferable to have a pure conversion library that really you absolutely cannot do anything but convert. And then if you wanted to do any kind of slicing or projections, then you would have to send it out to some library that knows how to do that and then get it back. In that case, whenever you send it to a library, you potentially lose features. The slicing and rebinning, what the Aghast slicing and rebinning are guaranteed to do is not lose any, not be lossy, and not lose any of the. For instance, you don't lose the moments just because you have rebinned your data. Mm-hmm. Whereas if you send it out to some library that doesn't know about moments, then you will lose them. So, and then secondly, what exactly is the scope? When I wrote it down, I said it's to convert histograms to histograms. And what I had in mind is histograms in one library to histograms in another library. But if you just say histograms to histograms, then that also includes these operations that we're talking about here. So yes, I'm very much on the fence about that. Yes, you've identified something that gnaws at me.
Following up with that, I mean, there's also things like scaling, and you can imagine certain situations where you might want to apply ufuncs to histogram contents, etc. So the scope can get quite large, right?
Exactly. I mean, so for me, the contradiction there is, I mean, you first told me that your user is not supposed to see Aghast, but on the other hand, provide tools to work with the intermediate representation of Aghast. So I mean, I'm not saying that any of this is wrong, and not telling. I mean, I have no idea what it should do. But I mean, I'm just saying that there's a contradiction between what you set out to do and what you have.
Yes, I think you are right that that it's a little bit disturbing. One of the things I've been thinking is maybe I should take this sweet slicing syntax and give it long names and make it all not user friendly.
No. I mean the slicing.
Thought about that.
You should.
No, I thought about that because you do use these in performing some of those conversions to various libraries. These are used.
But another aspect I can imagine, which is maybe related to this, is that as we go forwards, you might start to see packages evolve that really can only deal with Aghast. So a plotting library, for example, that could only plot if it receives Aghast. I can imagine that quite naturally evolving. And then maybe this sort of question becomes a bit, it's kind of related, right? Because then you'll see a package that's dedicated to plot Aghasts or it can only fit on Aghast. And I don't know, it's just something I can easily imagine happening and would probably tie into this discussion, right? Because it's functionality that is exclusive to this library, which was supposed to be a translator.
Right. In fact, Henry and I have been talking about hist using Aghast as its internal format.
There's one question I have. So you talked also, Jim, you also talked about the query service. And so in that sense, it does make sense if you can filter, on the data side, some of the data, right? So if you have, presumably if you have a library, you always assume that the data would come to the outside, where the user query is. But having Aghast will enable you to actually sort of remote control that filtering. Am I right?
You mean so I'm showing the diagram for the query service. We're imagining the user query being some bit of code, possibly Python, possibly a higher level language, and it uses, in its processing step, it uses some library, possibly hist, in order to define and fill all of those histograms, and then hist in turn uses boost-histogram. And then the thing that you get out, the thing that is internal to the machinery of the query system are these Aghasts, and it sends out a Aghast, and then sometime just before the user sees it, it turns it into a form that's more user-friendly. I don't see the actual slicing happening inside the query service, but definitely adding has to, because the query service will divide up some work among these 100 workers, and they all produce a set of histograms, and those histograms have to be combined somehow. So it absolutely has to be in scope to be able to add.
Can I lastly ask just about the schedule? Can you comment a bit on the sort of the current status and where it's, what's the immediate plans and
okay. So the first thing to say about it is in fact available. It is usable. And I believe it has all the converters for NumPy, one-dimensional root histograms, and pandas, and Fermilab column analysis tools, histograms. Obviously, the next step would be 2 and 3D histograms for root, including profiles. A major step will be replacing the pure Python flat buffers with C++ flat buffers that just talks to the Python layer. But these are all incremental improvements. So if you're interested in using this now, and particularly using it with pandas, you should be able to.
Well, Jim, if you're interested in including C++ in Aghast, we talked about that a little bit, but I think the distribution should be pretty easy to do to make it. That's what I'm hoping, at least with boost-histogram, but I think the same thing can be applied to the other scikit-hep projects, including Aghast if it needs a C++ part.
I want to point out that I think it does, because I've been playing around with it a little bit and finding the performance of the pure Python to be a bit slow.
Yeah.
Or at least no better than Pickle, I should say.
Yeah. Right. It should be. And it helps a great deal that there's a NumPy layer. Otherwise, it'd be much slower. Okay. So other questions? Because we are way over now. Right? Thanks.
All right. I think that finishes the meeting. Thank you, everyone.
Bye. Bye-bye.
Bye.
Bye-bye.
Bye.